Old DPRG member. I see there are some old faces here. So some of us go back, let's just say, into the last century, and we'll leave it at that. And I have not been roboting very much lately, so part of what I'm doing here is a sort of a recap of what I have done, or had done, bringing up to sort of current problems. These are all, I would say, ancient robots built in the last century, except for this one in the last decade. And the code for these robots is pretty much all online. If you go to www.geology.smu.edu and look for a link called Cool Stuff, there will be some robots off there, and there'll be more than you ever wanted to know about robot software. So I'm not really going to talk about the software very much today. I'm going to talk instead about sort of the motivations that led to these software and why you would want to spend the time to implement such things. Effectively, these robots, these 4 robots here, are all running the same code. They're all running sort of versions of the same code. So everything that I show with one applies to the other. For that reason, I'm going to do most of the demos today with this one, which is the Lego robot, one of the first ones I built back in the 90s. And it is, as you can see, made of Legos. And it has differential drive. That is, there's a separate motor for each wheel, and a caster and tail wheel. And you can see that that's a design that's carried through to these other robots. This one, which unfortunately is just a sculpture today, because I've got a bad battery in the battery pack. But if there's sufficient interest, I'll come back on another day with this one fixed, and we'll talk about the off-road robot. Even though it looks different from the same, it's effectively running the same code and it's doing the same kinds of things. It's a 2-wheel differential drive robot in a tread mode, and it has the same sort of sensors and so forth. So they're basically all designed the same, and they're basically running very much the same software. There's different implementations of it. And these are all like ancient microprocessors. These were all back when we had steam-powered microprocessors. And more modern versions, the implementations would be different, but the ideas are the same. So that's why I want to talk in kind of an abstract way today. These robots are all differential drive, and the advantage of differential drive is 0 turning radius. Look at this, I brought notes. I used to be able to talk just spontaneously, but I get lost these days. I have my notes. 0 turning radius is what we humans have. So if you want to build a robot that can run around in the same space that humans run around in, it's a useful thing to do. And that means that we can turn around pretty much in our own space. There's some tremendous advantages to being able to do that. It greatly simplifies your navigation software if you don't ever have to back up. Backing up is problematic. Even humans don't like to do it very much. What we do instead is we turn around so that our sensors and our manipulators are facing where we're going. So it's real useful to have 0 turning radius. Now, differential drive itself does not necessarily mean 0 turning radius. Go to my hand board here. If you had a robot, let's say, that was long and oblong, and it had differential drive wheels in the front and a tail wheel in the back, that robot would not have 0 turning radius, because it's going to rotate around a circle here, and this tail will hang out here and bang into things. So the second piece of the design for the differential drive is that the wheels effectively sit with the tail wheel on the perimeter of a circle. We'll draw that. So we have our imaginary circle here, and here are our drive wheels, and here's our caster and tail wheel. We'll talk about in a minute. If you look, all 3 of these, actually all 4 of these robots, have that same basic design. If we look here at SR04, part of what you'd like to do is keep the bottom real clean, because if there's anything to hang up on stuff, it will. This bottom was real clean until I added the grippers, which we're going to get to later on. But essentially, that's the ground clearance you have, and it has to do not only with the spacing above the wheels, but also with the caster and tail wheel. In other words, you can't go over anything that's any higher than that caster and tail wheel. And this one's got all kinds of gears and stuff in the bottom, and every time I turn it loose in my house, it comes back with, you know, dental floss and cat hair. And this is a bad idea. So if you can protect all that, that's good. This is one that I started working on and have never finished, but this one I think is pretty much the ideal design. We have quite a bit of ground clearance here. And we'll get back in a moment to how that one is set up. So all of these effectively work in the same way, which is that you want to have a circular architecture, a circular geometry that allows the robot to rotate in place and not bump into anything. And if you can do that, it simplifies a whole bunch of problems down the road. Secondly, with that geometry is where the center of gravity goes. Now, when you have a tripod like this, effectively what you've done, this is an equilateral triangle. And if we look at that from the side, you have a platform with a wheel in the middle, and we have a castering tail wheel. And here's our ground clearance right to this point here. Where the robot balances turns out to be real important to its performances. This three-wheel is not really very stable. It's really only stable on a flat surface. It's problematic when you get off a flat surface. If you really want to go outdoors, you have to have something that allows you a more complicated way of interfacing with the ground. But for indoor robots and things that are supposed to handle nice flat floors, it's a real handy geometry to work with. The problem becomes with where you put the balance point of the robot. And we'll look at the two limits. If the balance point of the robot is right over the axle, then you have maximum traction. That's what you like. You like the weight over the main drive wheels. These wheels are driven, this wheel is not. This wheel is just drug along behind it. However, this is not stable. This robot will tend to tip on its nose. Now, one thing you can do is you can put another caster up here. Prevent it from tipping up on its nose. That's problematic. What happens is, as soon as you try to drive up over a lip, you want to go from a hardwood floor on carpet, you lift your drive wheels off the ground. Mm-hmm. So, bad. Two casters, bad. If, on the other hand, you shift to the limit back here, if you put too much weight on the tail wheel, then you don't have enough weight over the drive wheels to get good friction, get good traction. And furthermore, when you try to rotate, when you try to steer, this wheel will tend to drag these wheels out of alignment if you have too much weight on the tail. If you can imagine that one of these robots is on a slope, then as the slope becomes steeper and steeper, eventually you don't have enough traction on the wheels anymore. All the weight is actually rocking back on the tail wheel. By the same token, if you're going down a hill, you get steeper and steeper, eventually it falls up on its nose. My experience has been that the ideal place for the center of gravity is about right here, which is, it's close to the axle, directly behind it, and below it as much as you can get. This robot here, I think, is pretty ideal in that case. It can't stay on its nose, even on a very steep slope. The way it's done here is, here are the motors with the wheels, here's the battery right behind the main axle with the tail wheel here. So we have enough weight on the tail wheel that it's stable. We've got enough weight on the drive wheels that we have good traction, good friction.
So you're saying about a third of the way back?
I would say just as close to the axle as you can get it. There's actually motors here anyway, but essentially just behind the axle. But as close to the axle as you can get it, and below the axle as much as you can get it. If you look on this robot, which has the same problem, the batteries are actually located between the upper and lower chassis plate here, so that they're effectively in line with the wheels. But it produces the same thing. What you want is a robot that you can turn loose and run around. This is my idea, so I should rephrase this. I want a robot that I can turn loose and run around, and I can sit in a chair with a mint julep and not have to get up and go chase it. So that's what we're going to talk about today. How do we get to that point? If the robot can get into a position where it's not stable, it will. So if you look at this one, that's not the only position it can get into. It can drive up onto something, it can get into this position. Well, for this robot, that's not stable either. Right, what about this position? Well, we're good. All right, let's look at SR04. The battery here is this lead acid battery right here in the back behind it. So it's not as low as I'd like it. But it can't stay up on its nose. How about back here? Oops, it's stable there. Well, if it's stable there, even though that seems unlikely, it will get into that position.
Murphy's Law says.
And you'll have to put down your windshield and get up out of your chair. So, for that reason, that's not a good design. This one also has another stability here. This is falling off. All right. That's all right, we're not using that one. So
on the first scenario where the robot is flipped, you still have traction on the wheels. So in theory, it should be able to. Well, not that is a tougher one, but in theory, it should be able to walk itself out of it.
It could wiggle itself free, yes. In general, if you don't have to wiggle yourself free, that's an advantage. So this robot won't stay in that position. It almost did, didn't it? So part of my background is building airplanes, and you always think about center of gravity in airplanes, so it kind of naturally transferred over to building robots. But you can solve a lot of problems if you solve the problems in hardware. You don't have to solve them in software. And there's a tremendous, I'm going to harp on that today a number of times. The other problem that we'd like to solve here is we'd like to make this geometry as accurate as we can. And it doesn't have to be perfectly accurate, and that's one of the reasons I'm going to use the Lego for most of the demos today, because it's not perfectly accurate. But on a robot like this, if, in point of fact, our tail wheel lays on the perimeter of our circle, and I should specify here that it only lays on the perimeter of the circle when we're actually turning. So when it's actually pointed this way, right? When we're going forward, the tail wheel actually drags out behind us. And that's good. It gives us a little bit more wheelbase. We get a little bit more speed. So when the robot is traveling forward, we have a little longer wheelbase than when it's actually rotating in place. And if you build your robot carefully, you get these things square, you get this equilateral triangle laid out properly, and the robot should have the ability to rotate in place without losing its center. Now there's no software running here. All I'm doing is ramping up and down the two wheels. I'm not counting in colored ticks. I'm not doing any kind of odometry. We're just increasing and decreasing the voltage to the two wheels. Once again, if the robot can stay in place on its own, then you don't have to do that in software. So that's a huge advantage. You can just tell the robot, rotate in place. And that's actually all this one can do. We'll let him wear himself out here.
You're lucky it stays in place, because since you don't have a stick controller running on those wheels, one could be running a little faster than the other. So
well, that's the point, is that you ideally like to spend the time on the mechanics, so that those parts work well, so that you don't have to go back and correct. Now there's some problems that are inevitable, one of which we'll talk about here is DC motors typically run slightly different speeds forward and backwards. And because of the geometry we're using here, we got one motor running forward and the other one running backwards. So if we tell them both go high speed, the robot won't go in a straight line. One will run very slightly faster than the other. In this case, I'm not ramping up to full speed. I'm ramping to about 75% full speed. But you're supposed to be impressed at how it hadn't fallen off the table. Yeah. That's all he gets to do. Okay, so we have a robot that has a certain geometry that's based on this idea that we're going to steer the thing differentially. We're going to steer it by having two motors, one for each wheel. We're going to have a caster and tail wheel that just drags out in the back. Some people have built robots in which the tail wheel represents the front rather than the back. So the robot would travel in this direction as the front. There's some problems with that. The chief one among them is that when you're trying to climb over things, you're trying to climb over things with an undriven wheel. And that's problematic. It's better to climb over things with the wheels that are driven. Mike Hamilton, that designed this outdoor robot, he said the rule is every wheel that touches the ground must be driven. Otherwise you're going to have something fall in a hole, it won't be able to climb out of the hole, and the other wheels are going to try to drag it out, and you get stuck. So you have the same kind of general concept here by having the tail wheel at the back. You're not trying to climb over things with an undriven tail wheel. The other problem is that if you think about the torque, when this robot is driving forward, the torque is pushing the tail wheel into the ground. That's good. When it's driving backwards, the torque is actually just torquing against the weight of the robot. It's trying to lift the robot up in the air. So when you drive over things, they tend to bounce up in the air a lot. So you're not nearly as stable. So the tail wheel in the back, or a caster wheel in the back. And think that's enough about geometry. Any questions about that? I'm going to cover about 30 topics here, and I'm not going to cover any of them very well. So please stop me. Feel free to stop me if you have questions.
Dave, what about a tricycle? I know that's a little off, but in that case, you would have a driven front wheel.
No zero turning radius.
Okay, thank you.
And what we're trying to do here is to build a robot that can move around in the same sort of spaces that we move around. That's the idea. So, hence the zero turning radius and hence the differential drive. Those relate to each other. So now just a word about the motor control. All of these robots use an H-bridge. They actually use a pair of H-bridges, one for each motor, which is a mechanism that supplies current to the motor, and we chop it up with a pulse width in order to control the speed of the robot. And I'm not going to go into that in detail. There's tutorials and stuff all over the net. But essentially, the way we're going to control the wheels is that we tell the given wheel that we have a minus 100 to plus 100 pulse width. And where plus 100 is full speed forward and minus 100 is full speed backwards. So if you want the robot to rotate in place, you drive one wheel forward and one wheel backwards. If you want it to move forward, you drive both of them forward. And we do this in at least for now, in a mechanism called open loop control, which I'm going to get back to in just a moment. But in point of fact, there's a slight detour in terms of the way that the robot is steered. We're not actually going to give it values for the left and right motor. That turns out to be clumsy when you get to higher level control. What we're going to do is we're going to give it a velocity and a rotation. So, two arguments that any process that wants to control the motion of the robot needs to come up with is it needs to say velocity and a rotation. The velocity is the velocity of the robot in the center, at this point right here. And the rotation is the rotation around that point. Now, in point of fact, it's real easy to get a left and right motor out of that. All we really do is we're going to say left motor is equal to the velocity plus the rotation. And the right motor is equal to the velocity minus the rotation. Now that seems like a fairly trivial point, but you can think of this then really, this is speed and steering. And when you get to higher level behaviors, it's much more handy to think about what the robot is doing in terms of the speed at the center of the robot and the rotations around the center of the robot, rather than in terms of what the left and right wheel is doing. It simplifies a whole bunch of things. So we have our little open loop controller here. I'm going to turn this guy on, and I'm going to tell him at about 60% pulse width modulation for velocity and a 0 for rotation, and he goes forward. And all we're doing is writing those values directly to the motor controller. And we do the same thing. This time I'm going to tell it a 0 for the velocity. I have to push some buttons here, so hang on. And I'm going to give it some value for the rotation. Some arbitrary value. Here we go. And if I know what I'm doing here, it should do the same thing that the other. Okay, so there's a rotational velocity but no forward velocity. Before we had a forward velocity but no rotational velocity. We can of course combine the two. Notice that the inside wheel there is not turning at all. Right? The sum of the velocity and the rotation is 0. If we slow it down some, that wheel will actually go backwards. And this is part of the power of specifying the control in terms of velocity and rotation. You see that wheel's actually going backwards, the inner wheel? But I didn't have to tell it to go backwards. I didn't have to make a conscious decision, this wheel go backwards. I just said, this combination of rotation with this combination of velocity produces that result. Well, that's one of the ways that it simplifies the
Question, what velocity you're
I think we know what sort of units you use for that, meters per second, whatever. What sort of rotation wouldn't typically be in meters per second, though? It'd be in. So
We're getting ahead of me, Paul. We're getting ahead of me.
Oh, sorry.
All right. Right now, we're doing all this open loop, and we're specifying the speed of the motors as simply a percentage of pulse width modulation. Okay? So the values that I specify for velocity and rotation while we're doing this open loop are just voltages. Now, that's problematic. We mentioned this earlier, because the speed of the motors is not really proportional to the voltage. It's actually the torque of the DC motor is proportional to the current. And we're faking that by saying, well, when I give you a wider pulse width, I'm giving you a higher voltage, and it's into a constant source, and so you get more current. But in terms of actually predicting exactly what the robot will do, that's not a direct correlation. Now, there's a bunch of problems with running this thing open loop, and I'm going to get to them, but we're going to do digression number one. I told you I wasn't going to talk about any code here, but I do have to talk about a little code. These robots all are programmed in what's called the subsumption paradigm, and you guys can go online and read about that ad nauseum. Effectively, it's a way of organizing behaviors in a hierarchy, where some behaviors are more important than others, they have higher priority, and therefore they have their commands to the subsystem. What we're running right now looks very simple, and I'm going to do this in kind of some pseudo C code. We have a while loop, that's while one, that's just a while forever. This is a forever loop. And we're going to have each one of our behaviors run internally in this loop. And then at the bottom of the loop, we're going to sleep for the remainder of 50 milliseconds. And we'll do that forever. So this is a loop that runs at 20 hertz. And that's the basic speed that all of these robots do their processing. It's a 20 hertz loop in which you can read your inputs, make whatever decisions you need to make, and write your outputs. Each one of these tasks does it in turn. And each one of these tasks has as its output 3 values. It has a flag, it has a command, and it has an argument. For our purposes, the command is the velocity, and the argument is the rotation. Now, right now, we're just running one of these, and I'm going to call it user. It's me. Its flag is always true. And the velocity and the rotation are the numbers I'm setting here with this mouse. So in the absence of anything else, the last thing in this loop is we're going to run an arbitrator that controls the motor. And it's going to take the flag of the highest priority task that's asserting and pass its arguments along to the motor control subsystem. I don't want to go into that in any more detail because there's a lot of detail to go into. If you go to this website, there are several ponderously long articles about how to do this and a bunch of the trade-offs you have to do. But this is effectively what we're running right now. So everything else is turned off except the user. And 20 times a second, we go through this loop, and the user has set these 2 values, that's me, has set these 2 values in memory, and those values are handed to the motor control subsystem. There are some problems when you do open loop control. And these have to do with the fact that it is open loop. That is, that you don't really know what you're doing. When I say run the motor at 50%, run the motor at 25%, we don't really know if that's the speed the motor's running. We're just guessing because it is open loop. And the likelihood is it's not the speed that the motor is running. Get some examples. Here I have a handy high friction surface. And I'm going to tell the robot to drive in a straight line at a very slow speed. Let's see how slow a speed we can drive in a straight line. I'd say that's too slow. I don't want to get it too fast because there we go. One thing you see right away is that we had enough torque to run on this nice flat friction-free surface. We don't have enough torque to run on this thing. At least we can't climb up on it. Suppose we had one wheel on it and one wheel not on it. Well, bam, we hit the tail wheel and we don't have enough torque to pull it up onto it, so it stops. Now let's help it there. It's not so obvious, but you can see that the robot is turning toward the car. Because we're sending the same signal to both wheels, but one of them has a higher friction surface, so there's more torque that's required to drive on that surface at a fixed speed. Turn the speed up a little bit, see if we can't get into a nicer torque range of the motor. Still can't do it. That's running at about 30% PWM. Here, I'll kick it up to about 60%. And we finally got enough torque to get up on it. But we still can't drive in a straight line. Okay, so that's one of the problems with open loop, but that's not the only problem. We can't hold slow speed very well. Now, why would you want to drive real slow like that? Well, it turns out with a differentially driven robot, the way you steer is by driving the wheels slower. So you may very well, in a complicated maneuver, need to drive the inside wheel in a turn at a very, very slow speed, but you want that slow speed to be accurate. So you can't steer accurately. Your behavior is different from one surface to another. Oh, what else? Behavior changes as the battery drains. I'm actually going out of order here. I didn't make this stuff happen first. I got a bumper behavior running, I got IR behaviors and photo behaviors running. But what happens is as you adjust the knobs in the course of working with it over the afternoon, your battery drains. And so you get it to all work just right. Now it's not working so well anymore because your battery is loose for your carefully tweaked numbers. And so you have these problems with, I would call it, repeatability of the behaviors that you're adjusting. You also have this problem of not being able to handle various surfaces. All of these problems are handled by moving from open loop to closed loop. Closed loop means that we're not just going to feed a voltage to the motor and expect it to go a certain speed. We're going to actually measure the speed that the motor is going. All these robots have shafting motors on the motors. These are these cool little, who makes these?
Pitman?
Pitman, thank you. Pitman motors that come with their encoders, and I actually machined some little gear heads on these. For the SR04, I'm not going to open it up, but they're buried down inside there. For the Lego robot, the encoders are actually these little paper wheels here that are on the end of the gear drive. I don't know if you can see that back there. This little paper encoder wheels that were printed on a laser printer. And there's a pair of Hamamatsu opto interrupters here. That little tiny chip there has a IR LED and a detector on it. And they're going to essentially generate an interrupt every time the wheel encoder passes that little signal. So we have a way, they're not mounted directly on the motors like they are on the other robots, but they're mounted on the gear shaft. So we have a way, we have a way of closing our feedback loop. When we give the control to the motor, we're not going to give it as a voltage anymore. This is your question, Paul. We're going to give it as a velocity. So, the way this is done is with a PID controller. And I want to take a few minutes here and demystify PID. It's a closed loop controller. Remember, we're going through this loop 20 times a second. So 20 times a second, we're going to count the number of encoder ticks that have happened in this last 50 milliseconds and stick it in a variable somewhere in memory. We actually have a couple of variables. One of them will be called the left velocity, and the other one is the right velocity for each wheel. And that's a number that's updated every 50 milliseconds, 20 times a second. With this robot, when it's at full speed with a full charge battery, I can get about 40 encoder ticks at full speed in 50 milliseconds. I like to define arbitrarily slow speed as 1/10 of full speed. So you got a car doing 60 miles an hour, slow speed is 6 miles an hour. So slow speed for this would be 4 encoder ticks for each 50 millisecond chunk. That's just about the limit of how many you need to do a good control. You get too few ticks, it gets hard to measure. So 20 times a second, we're going to measure how many encoder ticks have happened since since our last hearing. And we're no longer going to specify our velocity and rotation in terms of a voltage. We're actually going to specify it in terms of encoder ticks. Where full speed would be 40, 10 speed would be 4. Now that's actually kind of unhandy, so the software actually scales it back to plus and minus 100. Yes.
I'm sorry to interrupt, but you have been talking about these numbers like 20 hertz, 50 milliseconds. Are those limited to the hardware, or are these like the numbers that you would use even if you had a 1 gigahertz microphone?
All of these machines run at 20. That's actually not true. For purposes of this talk, all of these machines run at 20 hertz.
Yeah, okay, I understand that, but so these robots were built in the 90s, where when your microcontroller could run maybe.
I see your question. This one actually is set up to run at 50 hertz. And it can get away with that because it has encoders that give you jillions of counts. So,
Your PWM is not running at 50 hertz, is it?
no. The PWM, but as I said, I'm not going to get into that stuff today.
I wanted to make that clear.
Yes, the PWM's running at like 15.
PWM is not 20 hertz.
No. And that's the value that's generated. This is just
The rate that you update it and change it from one pulse width to another, even, yeah.
Exactly. That's at 20.
So what sort of rate are you running?
I think that
Yeah.
the PWM rate is like 15K on these.
Okay.
I forgot what it is on these.
So the reason why I asked is, so if you have a slow 50 cent microcontroller, you may want to go with 20 permutations per second. And if you have a $50 DSP, now obviously you can do more. The question is, do you want to do more? Will the robot get jittery, or will the control be lost if you do more or you do less?
For the ones I have done, as I say, this one runs at 50. These run at 20, and that seems fine. The more often you run, the shorter your window is for collecting data.
Mm-hmm.
So there's a trade-off, especially for some of the sensors that are kind of slow. And it has to do with the physical devices that you're working with.
Mm-hmm.
But if I had a faster processor, I'd probably still keep with these. I'd probably still keep it 20,
Okay.
at 20 hertz.
You can only update, you can only correct so much. If your PWM only responds at a certain range frequency anyways, you can't, you're sending too many commands for it to correct itself anyways. You really didn't even execute the last command if you're going faster than that.
Yeah, and there are physical constraints with what you can do. But there's one other, well, I'm going to do this in order. There's one piece I skipped here. If you look with the PID controller turned off, when you tell a robot to go, you see it just jerks and just immediately starts going. That is, we've applied whatever, 50%, 100% PWM immediately. That's real hard on gear chains. Motors can, you can sit there and slam the motor back and forth. At any given time, if you've got a gear train, the whole thing's just sitting on one tooth. And when you start slamming those back and forth, you can pop those things off, you can break gears, and you can do all kinds of ugly things. So there's actually another piece of code in here, which is a slew rate generator, a rate limiter. And essentially it says, how fast can I change the motor speed? You can go in and tweak that, but that also allows you to do some things that make the maneuvering a little bit prettier. And I'm going to turn it on right now.
So that's a slew rate directly in front of your PWM. In other words,
Yes.
side to side, when you jump from 0 to 100 on your scale.
Yeah, it'll only let you change it so fast.
Ah, okay.
So, and I think this will demonstrate here, if you watch it take off, you can see now that it accelerates. I've exaggerated it there
Yeah.
to make the point, so that we're no longer slamming them.
Now,
Slamming the motors around, which you really can break things and tear things.
Is
Interesting. Not to interrupt your talk. Sorry, somebody else talking?
I had a question. On your slew rate, are you essentially putting that into the command ahead of the PID?
Yes, actually, it sits in between there and the motor control subsystem. It just says that there's a limit, it's a function that if you were to draw it, it would look like that. It says if you're in this range here, you can pass the value straight through, but if you're above or below that range, we're going to clip how big a value you can pass in.
Okay,
Just so that- just so that-
and you're saying the motor control subsystem is where the PID is? Okay.
Okay.
Mickey.
So let's turn on the PID controller then and illustrate that it does indeed solve all these problems. He said hopefully. All right. Once again, I'm going to turn the speed of the thing down pretty slow here. You can see, as a matter of fact, it's really useful to hang on to the thing. You can feel it tug at you. And same thing now if we're trying to drive on two dissimilar surfaces. We can maintain a straight line because it's just going to increase the PWM to one and the other. That also means that driving in a straight line becomes an easier task because you don't really have to, and once again, the hardware can kind of do it for you. I'll keep the speed up here a little bit. Because we're keeping the speed of the two wheels the same. And if they overdrive, it'll actually slow down. It'll not only speed up and slow down. No censorship. No censorship.
Now that is as long as one wheel doesn't go into a puddle of oil and then start slipping, right?
Yes, we're driving on ice. Let's just say it doesn't do any better on ice than I do. Okay, so I said I was going to demystify PID just a little bit, and I want to do this in a really simple way. If you think about what we've done here, it's just like the cruise control in the car, right? So what we're going to do is we're going to say I want a certain velocity. Let's say I want 20 encoder ticks per unit time. And I'm going to test to see if we're actually going that speed. And if we're not, then I'm going to increase the pulse width a little bit. And I'm going to test again a 20th of a second later. And if we're still not, I'm going to increase the pulse width a little more. If you did this, we have an integrator. We're going to call it I. And we say, if our speed is too low, we're going to increment that integrator. If our speed is too high, we're going to decrement that integrator. That's a basic integral controller. That's really all there is to it. Right? We close our feedback loop by comparing the speed that we want against the speed that we actually measure. And we increase or decrease the pulse width to match that. Well, it turns out that this is actually not a real efficient way to do this. For one thing, it takes a long time to reach the set point. Say we're going 0 and we ask for 40, or we increase it by 1 and we really hadn't changed our speed any, so we increase it by another 1 and so forth. We'll slowly ramp up to the speed we want. But it's not very efficient. The more efficient way to do that is to actually take the size of the error itself. So I wanted to go 40 and I measured 0, so the size of the error is 40. So we're going to add that into the accumulator. Actually, we'll scale it by something and add that into the accumulator. So the accumulator will not be bumped up and down by 1, but rather by the size of the proportional error. And that's called a proportional controller. This means that when the error is very close, we wanted to go 18 ticks per unit time and we're going 17, that we're just going to add a small number into the accumulator. But when the error is large, we'll add a large number into the accumulator. That's a proportional controller. So we have our P and our I here. Our proportional controller is just like a spring. If you take a spring and you push on it real hard, it pushes back real hard. If you push on it just a little, it pushes back just a little. So you have a PI controller effectively modeling a spring, and it has the advantages of the spring and the disadvantages of the spring, which is that it bounces. It is, if we push the thing real hard and let it go, it doesn't go right to the speed we want. It overshoots. It goes like that. And we can solve this problem. This is like your car with springs but no shock absorbers. So we are correcting, but we're overcorrecting. And the way you handle that is you add in this third component, which is called the derivative. The derivative is just the difference between this error and the last error. It tells you how fast the error is changing. The derivative has this tremendous capability in that when you cross 0, when you cross the set point, the sign of the derivative swaps. So you can use it to damp out. And by adjusting these three values, the P and the I and the D, you can get your spring to go, which is what you want. A nice damped pendulum. You don't want it to overshoot. You don't want it to undershoot. You want it to, just like, so now we've got a spring and we added the shocks on your car. That's all you get for PID for today. It's actually pretty easy to use, and it's a real powerful control paradigm. You can use it for all sorts of things. You can use it for steering. You can use it to acquire targets, where you run into the same problem. You end up bouncing back and forth around acquiring a target. It's a very powerful unit. And effectively, when you're all done, what you're going to do is you're going to take your integral, your proportional, and your derivative. You're going to multiply each one of them by some scalar, sum them all together, and feed them back. And you get this real nice control function. And that's what's happening here.
So the second equation is I minus P minus D, or should I assume the only equation is...
I was getting ahead of myself. And again, you should just go online and look up how a real PID controller looks. I don't want to get into that too much. But essentially, your output is equal to I times a constant, we'll call it IC, plus P times a constant, we'll call it IP, plus D times a constant, IG. And these constants, you tweak until you get the thing to behave the way you want it. And a lot of that, there's not a correct way to do it. It's your taste. Do you want your robot to be real sharp and angular? You know, robot-like? Do you want it to be smooth and graceful? That has to do with how you adjust these numbers. This has nothing to do with the behaviors that are actually going to control the robot. This happens down below that level. This just has to do with the way the robot itself reacts to its own inputs. So, is that enough? Is that enough on PID? We could spend a whole day on PID. There's a lot of subtleties to it. There's a lot of stuff online. Okay, so we have our closed loop system now where we can read the encoders, tell how fast we're going, compare that against the speed that we ask for, and have a PID controller to manage all the in-betweens. We've also got the slew rate generator to keep us from slamming the gears around and breaking everything. And when we get to this point, we're very close to actually having a robot that can do something. At this point, we can drive in a straight line. Yes?
Back to a very early subject on the coaster, or caster rather. How do you keep it from getting tangled? That is, getting in an angle where it's trying to not work with things. Is it the fact that you have it on the circle that keeps it from getting into a...
It's the fact that it's on the edge of the circle, and it's also where you put the center of gravity. If the center of gravity is too far back, you have too much weight on the tail wheel, and when you try to rotate the tail wheel, will actually throw these wheels off.
Okay.
They'll cause them to skid sideways. So you want to get the center of gravity as close to you can here, and still not run into this problem of not being stable.
Okay.
So if you look at this one, you can see when we're actually rotating that it rotates in underneath the robot.
Mm-hmm.
You have to have enough room to do that.
Thank you.
So is this one with a flat front programmed to actually back up, though, if you run into a flat wall?
Oh, yes. Yes. You see the problem, of course, because here's the circle.
Mm-hmm.
But if we hit something here, we're already inside the circle.
Mm-hmm. So
So we'll have to back up a little bit to clear it. This is a much better design, because if you hit something here, you can actually get clear of it just by rotating. In general, you don't want to go backwards. There's no sensors on the back. You run into this problem of tilting up in the air. As a matter of fact, if you look here, SRO4, see this little plastic case there? There's a little steel ball inside of it. That's a tilt switch off of the pinball machine. That's totally so this guy can know when he's backed up over something and he's up in the air. It sets off that switch. I think you'll set it off if he cares. He doesn't care. All right. We'll get to that in a moment. I think that's everything I wanted to say about the motor control subsystem. Unless there are any questions, I want to go on now to the tasks that actually use those things. And what I'd like to do, I think today, I want to break this into two pieces. And we'll go over these behaviors here, and then we'll take a little break so I can take a leak. And can't last as long as I used to. And then we'll come back and actually some can collecting and show how these behaviors can be used to accomplish the higher level task. Basically, there are two types of subsumption behaviors. There are what's called servoing behaviors, which can try to approach or avoid something, and there are ballistic behaviors, which are sequences of things. Ballistic behaviors are real complicated and they're hard to make work right, and unfortunately that's where we're going to start here. But then we'll progress to some easier things. So I'd like to use a a paradigm here that looks something like the following. You have a sequence that begins with a raw sensor. And that raw sensor feeds what I'm going to call a virtual sensor. The virtual sensor is effectively some signal processing on the raw sensor. The virtual sensor then feeds a behavior. That's one of these things here. And the behavior has its output. For what we're doing today, all the outputs are just going to control the motor subsystem, so they're all just navigation behaviors, and they're all going to tell us we need a velocity or a rotation and give us a flag. So this guy is going to give us a velocity and a rotation and a flag to potentially be passed on to the rest of the system. This is an important distinction here. The raw sensor itself is the physical device that you're making, a bumper, an IR sensor, or whatever. The virtual sensor is the way you're going to interpret that information. It has to be processed in a certain way to be interpreted by the behavior. Then the behavior is going to make decisions basically about which way to drive, based on what it reads from these. So we start here with the bump sensor. This is, I think it was Dale Wheat one time said, bump sensor is the sensor of last resort. That's when all the other sensors have failed and you actually run into something. I'd like to think of it slightly different. The bump sensor is your sense of feel. It's the way you feel your environment. So when all the other sensors can't see, you're in a dark hallway, you can reach out and touch the walls and feel your way down the hallway. If you think about it that way, then if you think about it as collision avoidance, then every time you hit the bumper, it's wrong. It's like you shouldn't hit the bumper. If you think about it as feeling your environment, then okay, that's part of my sensing. That's my sense of touch. And all of these sensors that I'm going to talk about today are arranged in stereo pairs. We have a left and a right sensor, and that's how we do the navigation. In this particular one, and they're the same on these two, which I'll get to, you can see that there's a couple of marker switches behind this bumper here, and there's a couple more over here, and those are arranged in parallel. The bumper is actually pivoted in the center, because what you want to know is, was there a press on the left or the right? Presses in the middle don't tell you so much. If you get a press on the left, well, I need to turn right. If I see something on the right, I need to turn left. What do I do if I see something in the middle?
Head back.
Well, there's a lot of different things you can do, but what I'd like to say is, even if it's just a little bit on the right, I'd like to think of that as a right, and just a little bit on the left. Now, there's always the possibility that you'll run into the mount points themselves, so they're actually spring-loaded. And you will run into the mount points. It's just like the robot ended up sitting like this. It will do it. So our sensor, our raw sensor, is, if you look, it's a full coverage bumper. That is, there's nothing that the robot can hang on, above or below, that is not protected by the bumper. And the bumper will give you a press no matter where you touch it. And it's a very light press. There's not much required. No matter where you touch the bumper, you are fully protected. This bumper on SR04 is a little bit fancier, but effectively it's the same thing. You have a pair of micro switches left and right that are in parallel, and you have right and left presses, and these are mounted on, they're those little push buttons like you use to turn on the light in your closet when you open the door. You know, those things are hidden in the wall. But effectively, it's the same thing. You notice here I rounded the corners off because, oddly enough, those little sharp corners would always catch on things that the robot could otherwise actually get past, like a little tweak. I had to round off these corners. And once again, the robot is fully protected. You can't...
So speaking of that, why is the edge of the bumper it's seeming to extend beyond the extent of anything that's on the top of the robot?
You mean up here? It should just clear this guy. We'll get to this later on. This is a motion detector, and it actually can't see through the plexiglass. Also, it can't see when the robot's moving, so the robot has to deploy it when it's sitting still. It has its own little switches there.
Well, I'm just wondering, because on the Roomba has a rounded bumper on it, and that causes it to get stuck.
Well, and that's kind of what I'm aiming for here. One of the things I learned with these two robots Actually, I learned it best with this one, is that this one doesn't have a bumper. The bumper is a virtual bumper that it derives from its inertial measurement unit. The behaviors are the same. But the wheels are exposed here. And that's what I learned. You really want the wheels to be exposed. They're what's interacting with the environment. Here I've got the wheels all protected by a bumper. And that's not good. What you want is the wheels to be able to climb over things. So if you look at this bumper, it ends right in the middle of the wheel. See that?
Yep.
And the wheels are themselves the continuation of the curve. Note that there's nothing sticking out here. If you got an axle or a nut or something sticking out 1/4 of an inch, it will catch on things you drive by. And you try to go through a doorway, it'll catch on the robot. So you can't have anything sticking out there. Same thing here with these. These are, by the way, these wheels, these are cool wheels. These are from Mike's Hobby. They're for 1/4 scale airplanes. And they make really nice robot wheels. And they do good odometry because of the oval shape. So that would really be, I think, the better design.
Well, Dave, I was thinking about the curve on the top of the bumper, not the curve in this dimension, but the
You mean
curve,
here?
Yes. If you look at a Roomba, it's got it comes up from the floor and then it curves back, and since it has some travel in its suspension, it'll wedge itself under furniture.
Oh, is that right?
It'll because it'll hit the furniture and then go down because it's like a lever.
Well, these of course were tweaked in my house. So it has to do with, rocking chairs and the size of objects in my own particular house. And I sit in my chair with my mint julep and I watch them wander around and, well, it's stuck. Okay, how can it know and not get into that situation? So a lot of these little tweaks were made that way. I'm not sure I've seen that particular behavior. We did see it was having trouble with some of these chair legs, which I'll demonstrate here in a minute. Any other questions?
You were going from the raw to the virtual.
I was, and I'm going to go into our first behavior here, which is unfortunately a pretty complicated behavior. It's a ballistic behavior. You can go online and read about these things that go into more detail. Ballistic behavior is a sequence rather than a servoing behavior. The servoing behaviors are easier to understand and they're easier to make work, but that's not what we're going to start with here. So. Okay, so we have our PID controller running. And we have our slew generator running, and we've got each one of these motors with its H bits to be driven. And now we're going to have our bumper behavior. And the bumper behavior is really pretty straight ahead, and it's a classic bump and run from old style 1950s robots. And what that means is that when the bumper hits something on one side, that it performs the following sequence. If we hit something on the left, it's going to back up slightly. It's going to rotate slightly to the right. It's going to drive forward a little bit, and then it'll release control. So we've added a new behavior here. And while the user behavior was the very lowest priority, it's the thing that's going to happen when nothing else happens, the bumper behavior is the highest. That is, no matter what other tasks are running, if the bumper behavior says, I want to control the robot, it gets control of the robot. It subs in everything. So we set it up now. We have our user saying go straight ahead at about 75% full speed. And we have this bumper behavior turned on. And if the robot hits something on the left, backs up, rotates a little, and goes forward. If it hits something on the right, it backs up, rotates a little, and goes forward. Now that, go ahead, stick your foot out there, that's good. Don't let it go under your chair. That behavior will handle about 95% of all collisions. It's very simple, but it's quite robust. There are some problems with it, which we'll get to in a moment. But we're very close now to the ideal of just being able to sit down in your chair and turn the robot loose and let it run around. And a couple of questions to ask. How much should we turn when we hit something? Back up when I said we rotate a little bit. How much should it rotate? Well, the limits of that are, if we rotate a whole lot, let's say we turn around 180 degrees every time we hit something, you will get loose of the object. You'll definitely get loose of the object if you hit. But it makes navigation real hard. You can't, for example, go down a narrow hallway. You'll end up just banging around in the middle of the hallway. If you turn just a small amount when you hit something, then you're going to be pretty accurate about finding where you're going, but you'll run into other problems, which I'll illustrate here. most of these robots are set up so that typically, depending on the angle that it comes in, it takes 2 bumps to get clear of something. So essentially you're kind of feeling, you're going to try to get parallel to whatever it is you hit. See how confident I am just to lay right around? Oh, this is good. The problem with the standard bump and run, who knows the problem with the standard bump and run?
You get trapped.
You get caught and it's not just in corners, it's in symmetries. You get caught in geometrical symmetries. The corner is the easiest one to imagine. If you have a corner and you come into the thing and you bounce off one side, you just end up bouncing off the 2 sides. You're stuck.
Yep.
So this very robust algorithm that works well 95% of the time does not work in that case.
Yep.
Let's see if I can illustrate that. I'm going to try to make myself a corner.
An adaptive corner. A predatory corner.
I see what you mean. I seem to have lost a wheel here. We may have to move to another robot. Fortunately, I have one. All right, this robot, it could get caught in a corner, but that's just one geometry. As I said, it's symmetries. You can imagine another symmetry where it was under a table with legs and so forth, where the robot,
Yeah.
again, it's caught in a symmetry. It's doing the same thing over and over again. It can't get loose from that. So how do we solve this? All right, we're going to take digression number 2 here. I'm going to tell you I wasn't going to talk about software, but there's a couple of digressions here. And to talk about a control mechanism that's called a leaky integrator. Does that mean anything to anybody here? Anybody know what a leaky integrator is?
Leaky what?
Integrator. Leaky integrator. The leaky integrator.
Just one question before you go there.
Please do.
You were talking about how much should you turn, and you essentially said 180 degrees is too much, 2 degrees is too little. What's your algorithm for the right number?
Right now it's about 10 degrees. And what that allows the robot to do is, I say, typically when you hit something, it'll take a couple of presses to get free of it. Can we actually hit this thing here? So bang. Nope, didn't even one that time. What I'd like to do is,
Oh, you got your bad wheel there.
yeah, what's happened here? Somebody's not driving something. Something's loose.
Maybe you ran into the cords over there.
Yeah.
Not to.
Well, that's one of the problems with Legos is that the gears and things move around. We'll pull out SRL for if this guy won't do it. Let's see. All right, leaky integrator. What we have essentially, imagine you had a bucket full of water and it's got a hole in it. So the water's pouring out of that bucket and we're putting water into the bucket. So if we put water into the bucket at a slower rate than the water flows out of the bucket, the water will drain out. If we put water into the bucket at a faster rate than it's draining out of the bucket, the water will begin to build up in the bucket. We have a trigger point up here somewhere that says if the water builds up to this point, set a flag, we want to do something, we want to do a state change. I use these leaky integrators all throughout the robots for all different sorts of things. And effectively, it's a way of counting things in time. In the actual implementation of this, what you're going to have is inside of one of these little 20 millisecond while loops, we're going to have an integrator, and we're going to say, if that integrator is greater than 0, then decrement it. And that's all. So let's suppose we're decrementing that integrator by 1, and we're running it at 20 hertz. So if we put a 20 in that integrator, 20 times around the loop, it'll subtract 1 to it. 1 second later, there'll be a 0 in that integrator. Suppose every time we get a bumper press, we add a 20 to that integrator. All right, if we get a bumper press, and then a second later we get another bumper press, there's 0 in the integrator. We put 20 in, it drains away to 0. Suppose we get a bumper press, And half a second later, we get another bumper press. Well, now that 20 has just drained down to 10. So when we add in another 20, there's now 30 in the accumulator. The value has started to build. Now, half a second later, we get another bumper press. Now there's 20 in the accumulator, we add in 20, now there's a 40 in the accumulator. And suppose we're looking for some number, we say when there 100 gets in the accumulator, I want to set a flag. We've done something. We want to make a state change. So these leaky integrators, as I say, are used all throughout the robot code. And there's one running here for the bumper behavior. What it's doing is it's looking for that pattern where we're hitting the bumpers too fast. Okay, what do we do when we set the flag? All right. Well, there's a lot of things. We got to escape from this stuck geometry. There's a lot of things we can do. One of the basic things we can do is just change how much we turn. So instead of turning 10 degrees, let's turn 180 degrees. And then we'll reset our integrator to 0. Well, that's one way you can get out of it. Let's see if that works. If this seems to have a problem with my gear train here, we may have to use the other one.
David,
There's
I read,
2. There.
I read a book that had something like that, except they described it as having confidence values in different behaviors, and it would increment behavior, confidence values on behaviors when they worked well, and then decrement them when they didn't work so well. So depending on the values, it would change the priority of those different behaviors.
It'd be interesting to know how they defined work so well. that seemed like the hard part. We'll get SR04 here, I think. I haven't broken it in yet. Okay, so we get a left bump and a right bump, and we're stuck in a geometry. But we're counting bumps with our leaky integrator. And there it said, okay, that's enough. He also sets off a little audio alarm.
So if it was 95% robust without the leaky integrator.
Now we're at about 99.
Okay.
All right. Now it actually does something else.
What's the advantage of that versus using some random number for turning angle?
Okay, if you just used a random number for turning angle, you can't really navigate with the bumper. That is, if you want to, say, drive down a long hallway or find the perimeter of a room, then you need to have small amounts of turn. Now, if you have a small varying random number, that might work. You say, I'm going to vary it between 8 and 11 degrees. That might well work. And then you wouldn't have to have the state change to actually detect that you're stuck. If you can get rid of state changes, it's an advantage. Every time you make a state change, it's a vulnerability in the robot. And I'll come back to this later on, but if you think about when you make a state change, there's 4 possibilities. One of them is that the state change was required and you made it. That's good. The second one is that the state change was not required and you didn't make it. So that's good. The third one is the state change was required and you didn't make it. That's bad. The fourth one is the state change was not required, but you made it anyway. So you've got a 50-50 chance when you do a state change that it
Sort of
was
like
wrong.
that, throwing football, right? Passing football pass, right?
I don't see the analogy.
Throwing football, and there's only one good thing that can happen when you throw a football is the receiver catches it. Bad things are, you know, it falls on the ground or
Yes. So
somebody intercepts it or
if
whatever.
you can write the code so that you don't need to do state changes, that's an advantage because you don't get into the situation where you're doing it at the wrong time or not doing it what's required.
Can you explain how the repeated bump, how the leaky integrator interacts with the repeated bump to trigger the back off and turn 180 degrees? Does each bump add 20 to the leaky accompaniment?
Each bump adds 20 to our leaky integrator. And if the next bump is a second later, then the accumulator never builds. But if the bump is less than that, the accumulator begins to build. And then all we're really doing when we set the flag is just changing the amount of the rotation in the normal. Instead of saying rotate 10 degrees, we say rotate 180 degrees. Now it's actually doing something, SR04 is actually doing something a little slicker than that, which is, you ask, how do we know how much to turn when we do a bump? Well, on SR04, the amount you turn is determined by how much is in this leaky integrator, even before you hit the trigger point. So you turn less as the integrator fills up. All right? What that means is, if there is enough room to get through the space, it will. It'll actually find the center. Let me see if I can demonstrate that. I'll do the same thing with my legs here, but I'm actually going to make it big enough that it can get through the space. Is that big enough? I'm going to hit my jeans. And what you'll see is that it's turning slightly less each time. See that? So that if it can center up and get through there, it will. So that it can actually negotiate through a very, very small opening. And so it'll try that for a while. But if the counts get too high and that flag is set, then it gives up and says, okay, I'm just going to turn around. I can't get through there.
So this leak integrator is like a watchdog timer kind of deal.
Well, except you're using the value other than it just than it hit the value.
I guess you could implement it in different ways, really, but since you're running, you're driving, and that's occurring over a period of time. I'm backing up, moving forward. That's happening in time. And what you're doing makes sense, but I guess another way to do it would be if I just recorded how much I move around and keep track of, it's really doing the same thing where you say, I haven't moved very far, and I keep racking up.
Yeah.
The same thing.
Yeah, you could do the same thing, just say, I'm about in the same spot.
Yeah.
Maybe I should do something different.
Right.
Yeah, I should try a different behavior. Which, actually, I wish I could. We'll take a break in a minute, and I'll see if I can't make this thing work, because he's got some other behaviors that I can't demonstrate here, unfortunately. All right, you get this working. You have the robot control subsystem. You've got a full coverage bumper. It can give you left and right stereo detections. We have this ballistic behavior running, which does this very simple bump and run, but looks for these other oddities. You now have a robot that you can turn loose. You can just turn it on and sit down, have your medjool, put your feet up, and let it wander around and it won't get caught. SRO4 has actually a bunch of other pretty sophisticated behaviors. It knows, for example, if something gets jammed in under the bumper, it knows how to get free from that. It knows how to get untangled if it gets wadded up in things. I don't know if I can demonstrate those here. A bumper press should just be a quick thing like that, because you immediately back off. So if the bumper's jammed, okay, it's going to back away. No, it doesn't like that. Turns on alarm, try to shove its way forward. That didn't work. Try to rotate and try to back off. It's going to try to unplug that bumper. SRO4, I should stop here. SRO4, one of the things I learned on this robot is it's real hard to tell what the robot's doing. You get a whole bunch of sensors going and everything. Who's it reacting to? So I put LEDs all over the thing. So if you get a bumper press on that side, it actually turns on an LED. You can sit across the room and say, I got a left bumper, a right bumper, I got a center bumper. All right. This whole thing is covered with LEDs, and we'll get back to that in a minute, but it's real useful when you're watching the thing. You can tell which it's responding to, what is it responding to. So at this point, we can begin to add some of the other simpler behaviors on top of that. And as I say, the escape behavior, which is what it's doing here to get loose from the geometry, is quite complicated. It's the most complicated behavior on the robot. It's a little odd that would be the first behavior that I implemented, because it really is quite sophisticated. However, when you get to that point, you have a robot, as I say, you can turn loose. And will wander around your house and not get stuck. Wander around your cluttered environment, knows how to get loose when it sucks up a gym sock up in under the bumper, or whatever the appropriate is. So any other questions about that?
Yeah, this behavior for the bumper, the ballistic behavior, how many steps is it?
I really recommend, I've got it detailed online in the code. I really recommend you go and look at that. But effectively, it sits in a loop monitoring to see if the bumper has been pressed. And if the bumper has been pressed, it goes into the first ballistic state, which is to back up. And then it goes into that for a certain period of time. And then it goes into the second state, which is to rotate. And the third state, which is to drive forward, hopefully to clear whatever we just hit.
Mm-hmm. And then that's the exit of the ballistic behavior.
Yes. And so what's happening here, if you think about the subsumption, is that our user behavior is driving the robot straight forward in the absence of anything else. As soon as it strikes, it's subsumed, and then there it takes back over. So it just continues to drive the robot straight. Okay, with that basic structure there, as we add other behaviors, we're kind of bulletproof, because if they fail, the bumper behavior will balance out.
Yep.
And if the other behaviors are working well, we shouldn't run into anything. But they all have their blind spots and so forth, and so you do run into situations where, even though we're doing nice navigation and shouldn't be any other objects in the way, you do run into them, and the bumper will always be the highest priority. Whatever else we fill in here, the bumper will always be the highest priority, so it will always take over from the other behaviors. Okay, I think that's all I want to talk about that. We've covered the leaky integrator and how the leaky integrator is used to count events and how we can use that to control things. In this case, we're both using it to set the trigger when the integrator fills up, and we're also using the actual value in the integrator to control the amount of turn. That's what allows it to slip through the small spaces.
And are you using a leaky integrator to detect the trapped bumper where the bumper is permanently stuck?
Yes and no. Effectively, what it's doing there is the routine that's looking for the bumper to be pressed actually checks 100 times a second. And if it sees that the bumper is pressed in a sequence of those, so it's like the leaky integrator, then it triggers it, says, yeah. Well, it's effectively the same. It's not actually happening in the same way. Well, the easiest behavior, as I say, this is the most complicated behavior, this bumper behavior. The easiest behavior to make work is a photophore behavior. And the way that works is, if you look here on SR04, you can see there's 2 cadmium sulfide photocells. It's the same thing on this guy underneath this little hat here. Those are essentially variable resistors whose resistance changes when they get light on them. So, and I believe the ones on here, I got these from Tanner's, and I think when they're in the dark, they're like 5 megohm, and when they're in the light, they're like 5K or something like that. They form the upper half of the voltage divider. So this is our raw sensor. And we got a V plus here. We've got our variable resistor, and we've got another resistor, and we're going to read this with an A to D converter. And that'll give us a value that tells us how bright the light is. Our virtual sensor in this case, actually we have 2 of these. Once again, we have stereo left and right. We have one pointed very slightly to the right and one pointed very slightly to the left. So what our virtual sensor is going to do is going to read those 2 values and difference them. And if the difference between them is large enough, it's going to request that we turn toward the brighter side. So it'll set its flag and it'll say turn left or turn right, whichever side is brighter. For this robot, it's these little green LEDs here on either side. I don't know if we have enough light difference in here. Let's find out. And you can see this green light here came on, so he thinks he's brighter on that side. Now he thinks he's brighter on this side. So that should be enough to run. And this is what's called a servoid behavior, in which case we're just going to turn in the direction. All we're running is we have this bumper and we have this photo behavior. Actually, photo behavior, and we've got the bumper there to go inside. Photo behavior is kind of cool because in a human environment, we tend to light the areas where we walk. You know, you light the hallways and it's dark in the corners and so forth. So if you just turn it loose, you can go around and find the brightest parts of the room. It's just pretty intelligent too. If you go around in the areas where humans tend to habitate. I took SR04 into a mall one time, and you know, malls have all these little pools of light everywhere. And it was really cool. When it would drive under one pool of light, it couldn't see that light anymore. It would see another, and so it would navigate to the next one. We ran it for about half an hour until the guards came and threw us out. The guys here last week, I don't remember exactly what they said, but I'm pretty sure what the guards said was, "Hey, we don't serve their kind here. Your swords will have to wait outside." or something to that effect. I can't play.
Must be dark.
All right, now, we're actually turning toward the brighter side, but it's just a simple switch to turn toward the darker side. Go to the dark side. And in that case, what happens is that the robot will seek out the darkest place in the room rather than the lightest place in the room, which is pretty cool. Unfortunately, in practice, when you tell it to seek out the dark, what it does is it ends up banging around under the couch or something. You know, it's not nearly as interesting to watch as seeking out the light. But that's a real simple behavior to get working, because all we're really doing is saying, look at our left and right sensor, and whichever one is brighter, issue a turn to that side. And then 50 milliseconds later, do it again. So it'll continue to turn until the light between the two is equal. Can I bring a flashlight? Yeah. You can, for example, make him follow you.
Now, are you using a proportional signal or just one is brighter than the other?
Just one brighter than the other. Okay, with just these two behaviors, with our underlying PID control subsystem, and we have something that can seek on light, especially if you have a house that's got like a lot of lamps and maybe little pools of light here and there, you can actually do some pretty cool things. And I won't go into detail right now, but there are certain geometries that you can force the robot can do very, very intelligent appearing behaviors just by following light or by avoiding light. You can also, the robot can turn these behaviors on and off on its own. So it can decide to turn on the photo behavior at a certain point. Any questions? As I said, that's the simplest behavior to get ready, though. It's a fun one to play with. All right, the next behavior we're going to look at is the IR behavior. IR is complicated in this step right here. There's a whole lot of signal processing that goes on. But effectively what we're doing is the same for all these robots. If I can get this guy to work. I say, turn on your IR. What you have here is in the front bumper, there are two infrared LEDs in this little shadow box here. And they project sort of a oval space out here in front of the robot. And then you have these little silver boxes here on either side, which are infrared detectors. And infrared is kind of complicated. You actually have to modulate the infrared LED at 40 kilohertz in order for the detectors to detect them, and then that's further modulated at 100 hertz. And the rule says that when I turn the LED on, I get a detection. If I turn the LED off, I don't get a detection. Both of those things are required to call it a detection. That way it can't be swamped by sunlight or something like that. In point of fact, it's a little more complicated than that. There's a leaky integrator in there, because we're actually going to count the number of detections. And if we have a whole lot of them, we're going to reduce the sensitivity of the IR. If we just have a few of them, we increase the sensitivity of the IR. So when it gets into what I call a sensor box, you got in a space like this, where everywhere you look, there's an IR detection, so you're effectively blind. You reduce the sensitivity of the IR. When it's out in an open space, it can go up to high speed, turn the sensitivity way up, look out as far as it can. So, you turn this thing on, and we've got some little LEDs back here in the back. You can see right there that green one came on when it saw my hand. See that?
Mm-hmm.
All right, and on this side, there's a red one when it saw my hand. Mm-hmm. And here, both of them see my hand. Is that obvious? Everybody see that? Mm-hmm. Hold it up like this. So, there's that one, and there's both, and there's that one alone, and there's neither. You can see out to about 18 inches. And the pattern here on all of these, here we have our robot, and we have two overlapping loads of IR detection, like this, the left and the right load. So they're like bunny rabbit. And the way these lobes are created is they have to do with the overlapping of the IR illumination and then these two detectors which are looking left and right. Once again, we have stereo detectors, a left detector and a right detector. The behavior for the IR is not markedly different than the behavior for the photo. except that we're not going to turn toward the detections, we're going to turn away from them. So the same thing, if I see a detection on the left, I'm going to turn right. If I see a detection on the right, I'm going to turn left. In addition, and this is real important, we're going to slow down. If I see a detection on either side, I slow down a little bit. If I see a common detection in front of me, I'm going to slow down to 0. But I'm not going to alter my rotation value. Now, this is real key. My velocity will go to 0. I won't be making any headway. But I'll continue to rotate. I can't make headway as long as both of the detectors see something. But if I begin to rotate, one or the other of those detectors will clear. And when it does, I'll start pulling again. See if I can.
What if the rotation happened to be 0 when they both see something?
It takes whatever the last rotation was.
Okay.
Yeah, I got a gear shaft broken there. That's too bad. You know it. Best laid plans.
So is this considered ballistic or servo?
This is a servo. Let's make this guy do it here. In this one, you see we have a left and right. I should illustrate that. I have a left and right red light. So, you see the one on the top there?
Oh, yeah.
And here's common. Right.
So that's basically a long-range bumper.
Okay, we slow to 0, but we can still rotate, right? In this case, we're driving straight. That's this low-level guy here, telling us to go straight. And we're subsumed, we've added a layer into it, which is the IR. You get the IR working well, we don't run into very many things anymore. One of the things you'll notice in my robots, I generally don't have them go very fast. I found fast is the enemy of smart.
So how about the position of the sensor? Do you want it to be at the center, at the sides?
What I really like is to have as much coverage as you can. You don't want to see the floor. Have as much full coverage as you can. It's just like the... Hey! You brought us something.
Catch. Brought you your socks.
Yeah. And of course we can combine all these. You see right now that the bumper behavior, of course, is running the whole time. And if the sonar runs, or the IR runs us into something, then it's immediately subsumed by the bumper. Bumper's not, sorry.
Fool it.
So when the bumper's running, the IR is not running.
Well, it's still running. And it's still saying, I see something on the left, I want to turn left, I want to turn left.
It says ignore it, yeah.
I think it's subsumed.
That's not an LED light that's coming out of the
I can't remember, they may actually be suppressed. But they should come on. So suppose then, just by way of example, if you turn on the photo behavior, which on this robot is going to be these little green lights. Sees anything. So there's the user, it says drive in a straight line. And there the IR says no turn. And there the photo came on and says, well, I want to go toward this light over here.
Which does the highest quality, solar or the
The bump.
The IR, the IR has higher priority. The bumper is the highest, next is the IR, then the sonar, and then the photo, and then the lower level behaviors that we'll get to in a minute.
You said you increased or decreased the sensitivity of your iron reading. Is that just determined by the confidence of how many false readings you think you've gotten?
Effectively, we're using another ET integrator. So you're just saying how many detections have to be in that ET integrator before I can get it as a daily detection. And when it's insensitive, just one detection is going to do that. When it's very sensitive, multiple is required.
Okay.
Just varying the count of how many detections. He likes you.
Could be.
Okay, well, one of the things I'm trying to illustrate here is how all these behaviors are running at once, and they're actually all interacting with each other. So you get a fairly complicated navigation of the robot by the way these behaviors interact with each other. And I think that's all I want to talk about the IR. Once again, IR is one of those things it's pretty hairy if you get real deep into it. And there are a lot of different ways to do it. But effectively, what we're doing is we're breaking the space in front of the robot up into these two lobes. So we have a left and right, and we're just saying, is there something in one or the other that does not?
And you could add more sensors if you wanted more precision navigation.
And if you look here, there's actually two more. There's two side-looking IR and this guy. Maybe I can, let me take a break here, figure out what's wrong. This actually has side-looking infrared distance detectors, so it can do wall following, which is one of the things I'd like to illustrate here.
Is there a practical way of tuning where these things are pointing, or is it like trying a letter by you move your hand until you
Well,
get...
I actually did it with a VCR box. And I turned the thing on and then scoop this box out in front of it and find, until the light came on, I find the boundaries, and that way I can adjust these things. And that's how I came up with these two overlaps. As I say, it's about this big. I think the furthest out that it can see is about 18 inches, and you may not be able to see that far on this. Yeah, something like that. Okay, well, there's actually two other modes I wanted to get into here, which I don't think I'm going to be able to illustrate. And then I thought we'd take a little break if you guys are so inclined, and come back and we'll do some can collecting with SR04. So when I got to this part with the robot, I had photo and infrared, and I actually added sonar, and we'll get to the sonar here. They work very much like the IR. They give us two lobes, except these lobes are 15 degrees wide and they go out to about 30 feet. So we have a whole lot more precision. We also know not only that there's an object there, but we know how far away the object is, which is a real useful thing to know. When I got to that point, I went back and I added in position calculations, which is what I want to talk about now. And we'll talk about those just briefly. If you remember when we were, my drawing is gone now, when we were building the PID controller, we measured the wheel encoders 20 times a second to see how many encoder ticks had elapsed since the last 20th of a second. And we use that to control the speed of the motor. Now it's actually doing something else that I didn't cover at that time, which is it's calculating its position from those as well, with a mechanism called odometry. Effectively what we're doing is 20 times a second, we count how many encoder ticks the left and right wheel has gone. And we use that to construct a little right triangle to tell us where the robot has gone during that time. And those are actually just printed out here in terms of inches. The way this robot, all these robots are set up, wherever it's turned on, and I set it down and turn it on, it's in a coordinate system that's at 0, 0, 0, where this is 0 in y, and this is 0 in x, and this is 0 in theta, its rotation. So simply by hitting reset, I set all those to 0. I, for convenience, do this in inches, being an American boy and all. And even this robot, when it goes out and does a trip of a mile, it's doing it on a coordinate system in inches. So it goes 60,487 inches, whatever it is, through the forest and turns around and comes back. So they're all specified in inches. And at this point, this is our raw sensor. Our raw sensor is simply a calculation of the robot's current position in X and Y and theta. With X and Y in inches, and theta is in radians. So if you run the robot and you look at these little numbers down here, as it runs around, it's keeping track of its position. It says here that it's gone 41 inches forward and 22 inches off in X. And it's just tracking that position constantly. If you drive back over here to where it started, those numbers should go back to 0. I'm going to turn all the other sensors off now, so we won't be confused, except I will leave the bumper running since we need some protection. So what do we do with this raw sensor? We have a raw sensor that 20 times a second gives us the location of the robot in X and Y. We're going to do some virtual processing to that, and we have several different behaviors that can use that. One of the simplest behaviors is something that looks exactly like what we've already seen for the IR behavior, whereas we're going to turn away from the detection. The way this works is that I'm going to tell the robot that it's inside of a box of a certain size and shape. I believe the one that's set up here for default is 5 feet wide and 10 feet long. And then I'm going to remember this value right here, X, Y, and theta, is the center of the robot, right here. So using the location of the center of the robot, I'm going to calculate 2 virtual sensors. One out here and one out here. So I'm going to calculate 2 points that are like, I don't know, 8 inches in front of the robot and about 25 degrees on either side of the robot. And I have a piece of code called bounds, boundary. It's a little function. You hand boundary a bounding box, which is specified by X and Y coordinates, and you hand it a location, and it tells you if that location is inside that bounding box. Yes or no. It gives you a true or false boundary. I actually handed a list of bounding boxes so you can have a complicated space. And you hand it the location of the robot, it will tell you whether or not the robot is inside this bounding box or outside the bounding box. Okay, so we have 2 stereo virtual sensors, one out here and one out here. And 20 times a second, we're going to calculate what that position is based on where we know the robot to be. And we're going to call this bounding box routine and we say, is either one of those dots inside the box or outside the box? That's our virtual sensor. Once we know whether it's inside or outside the box, we're just going to run the same code that we ran for the IR. That is, we're going to slow down and turn away if it's outside the box. Oh, let's see if we can do this. Bounds. And do I have to tell it which box? I guess I do.
This is a 5 by 10 box?
5 foot by 10 foot box. I've got a 4 foot by 8 foot box for that little one that's broken that'll stay on this tabletop. I came by earlier this week, I can stay on the tabletop for 3 minutes and not fall off it. Now all this is doing is effectively the same code we were running before. When the bounding box code is not running, the robot is just doing this, whatever the user told it to do, which is to go straight ahead with 0 rotation. But whenever either one of those virtual sensors crosses the line, then it executes the avoidance behavior.
So basically it's like a mine.
Say again?
It's like a mine inside of a box. Like the mine.
Yes, you're right. This is Marcel Duchamp walking against the wind.
But now, do you still have to have the user behavior to have a forward motion?
Yes.
Okay.
Yes. Matter of fact, there's a kind of neat thing you can do. If you set the user behavior to 0, so when nothing else is running, the robot comes to a stop, then, like if you reach down and hit the bumper, it'll move away from it. Or if you put your hand down into the IR, it'll drive out of the IR, and then it'll stop. So you can turn it loose like that, turn all the sensors on, and it'll move around the room until it finds a place where there's no sensors, and then it'll stop, just like a dog. And then you turn on the light switch, or somebody walks in the room or something, just get up and move. And go find a new location. There's something else going on here. This thing's going to run for 3 minutes, and then it's going to try to find its way back to where it started. I think. In this case, the robot is using the virtual sensor exactly the same way that it would use a real physical sensor, like an IR detection or a sonar detection or anything else. But it's this imaginary line there that has totally to do with where the robot's location is. Other than that, all the code and everything is the same. Even though it looks like it's doing something much more complicated here, it's not. It's actually just running the same piece of software. We made it to 3 minutes yet? Seems like it should have quit by now.
When you're waiting for 3 minutes, it goes very slow.
It's got a clock in it.
How do you detect wheel slippage without a driver on?
You don't. It turns out, a lot of people I've talked to about odometry that have worked with it, and you go off because it's not perfect. Let's say it's not useless. But, you know, if you turn the robot loose in your living room and it ran around for half an hour and it came back, okay, it missed where it started by 4 feet. Still made it back to the living room. That's pretty useful. You know, I've found that they don't have to be perfect to be very useful. There he goes. That's not far. That's pretty close to where he started. When if I make this one work here on the tabletop, I actually have a mark here on the tabletop. You can see that. This is very valuable. This is the David, don't forget I'm turned on and draining the battery song. Just to let me know.
And when that time is up, what is the return to home?
Well, that's where we're going right now. So we got bumpers, we got IR, we got photo. And this behavior was called boundary behavior. And these are roughly the order. The higher up they are here, the higher their priority is. Okay, there's another behavior that we can use this same odometry information. Rather than doing this boundary behavior where we're going to stay inside a box or a set of boxes.
Just
if, for example,
send them to zero.
If we had, let's say, a flower garden that you wanted to keep the robot out of, or a pool of water, you could set a boundary box that would, without any detector, know where that water is. You just say, just don't go over there. You know? And so it can be combined with these other behaviors. The navigation behavior is separate and distinct, and while this behavior, the boundary behavior, is analogous to the IR, that is, we're turning away from detections, the navigation behavior is analogous to the photo. We're going to turn toward our detections. The way we're going to do it is we're going to define on our XY coordinate plane, kind of point out here in X and Y. And we have a little piece of code that we run that says the robot knows where it is, and we're giving you a point out here in space, and I want this routine to return me how far away that point is from where we are, and whether it's left or right of me. That's all I care about. Is it to the left or to the right? If it's 10 degrees to the left, if it's 50 degrees to the left, it's to the left. That's all I care about. So we'll do the same thing we did with the photo behavior. We'll test to say, is our target left or right? And if it's to the right of me, I'm going to turn right for 50 milliseconds. And I'm going to test again. And if it's still to the right of me, I'll continue turning right for 50 milliseconds. And then I'll test again. If it's directly ahead of me, I won't do anything. So this behavior, which we'll add here, boundary navigation, requires us to have our virtual sensor that gives us our location. And then we have to have a target. I'm sorry, our raw sensor. We have to have a target. And the virtual sensor returns us a bearing and a distance to the target. After that, we essentially just run the photo behavior. It's very simple. We just turn in the direction. So, I'm going to turn off the boundary behavior. I'm going to turn on the navigation behavior. I'm going to tell the robot to go to a point. Oh, I wish I could demonstrate this one. This one does fancy stuff. It does a lot of extra fancy stuff that I'm going to have to explain. I'm tell it to go to a point that's 8 feet out in front of it. Turn around, come back. started about there.
And you developed all these before we had the Quick Trip or any of those?
Now, it actually came to a stop there, and it's going to rotate back toward the new target. That's real complicated, and I don't want to get to that yet, but I can't turn it off on this one. I can turn it off on the little one.
So the other one would just sort of meander around?
When it crossed the point, it would have kept going, and I think I can make that one do this here. And he sets off a little bell. Now, it's important to realize that it actually really is navigating. It's not just orienting on the point and driving in a straight line. And we can illustrate that. I'm going to turn on the infrared avoidance. Oh, let's see, maybe I can turn that off. No stop. Makes total sense. Okay, so he doesn't slow down here. He just drives right through the waypoint and grab the next waypoint off the list. He may not turn it as he keeps going. And he continues turning until the waypoint's in front of him again. And as I say, it really is navigating. It's not just driving in a straight line. And you see the IR subsumed it there for a minute. Now the navigation takes back over.
So the command is to return home, basically.
In this case, it's going just between, there's a list of waypoints, and it has 2 points in the list, 8 feet out, and then 0 here. If, for example, I'm going to tell it to go ahead and stop when it gets to the location. Oh, forgot to tell it where to go. Sorry. What in the world is it doing? This bumper press I'm giving it here is what selects, there's a whole list of different types of targets. And I said select target number 1. I just forgot to do it.
Still trying to go to that point right there, 8 feet out.
Yes.
Okay.
And if there was things in the way,
We're back out of it.
so as I say, 20 times a second he's recalculating and just saying, should I turn left or right? It will even come in from the back. I think we're going to go around the table. Cool. So you can see the navigation is saying, I need to turn that way, but the IR says, no, you can't. There's an object in the way. Now the IR says, okay, you're clear. Go ahead and do what you want to do. So it tries to turn and go back to the object, but nope, there's still a table in the way.
Now that's the side IR?
No, that's just the normal front-looking IR.
So if I put a giant walnut shell over that penny right there, it's pretty well doomed, isn't it? That's why you need vision on your new Android phone.
That's right. Not bad. Not bad. it's easy to, because this thing is going to waypoints that are straight line segments,
Yeah.
it's easy to think of in terms of straight line segments, but that's arbitrary. So for example, if we have 8 feet here, I tell the robot, I want you to go straight forward 8 feet and come back. Do this in my house. Take the living room, point it straight at the wall, just right in the middle of the wall, and say, go 8 feet forward. It'll drive all the way around the house. Go through the kitchen, go down the hallway, come in, loop back around, come in through the other door, and make it to a point 8 feet on the other side of the wall. So this looks like fairly common. If you go online and look at the J-Bot, when it's navigating through the woods, to a point a mile away, it's doing exactly what this is doing here. It's told one point, there's all those trees in the way, there's picnic tables and all this other stuff. It's single-mindedly going toward that point and avoiding things in between.
That little beep indicating it arrived.
That it arrived at the waypoint, yes. Yeah, beep's a little flashy LEDs. If you just watch the robot maneuvering, it's real hard to tell what the hell it's doing. You know, it's just turning left and right and starting and stopping. So I cover the thing with LEDs to try to. And we ought to be able to do the same thing here. There's another routine that tells it to go 24 feet. I bet if we set it up right here, you think, is there enough room to make it through? I don't know if there is enough. Tell it to go 24 feet to a point straight back over there. Let's see if it works. Does it look like I can get 24 feet that way? Yeah. Is there a clearing back there? It's nice to point at a nice big open area. This is the same thing with J-Bot. When we took it over to Fair Park and we run around Fair Park, so I'm not trying to hit this particular GPS coordinate right exactly here. What I want to do is see if I can hit that field over there. You know, it's a quarter mile away and the field's 100 yards on the side, so I can probably hit the field, even if my odometry is way off. I don't know if I could hit, you know, a little target. All right. That's 24 feet. All right. We might have to help you a little.
See, even if it's you're going to get back to that point and still go this way instead of going that way.
You could. And there's a... This is maybe beyond today's discussion, but there's a way to solve that problem. There's a singularity in waypoint navigation. It has to do with exactly what you get to begin with. What happens when you're trying to make it to a point here, starting here, and there is a concave barrier between you. What will happen is the robot will go toward it, the sensors will drive it away, and it'll just continue to do this. It'll never make it to there. So, unfortunately, I couldn't demonstrate it because this guy is broken. But what you do at that point is you go into wall following mode, into perimeter following mode, and you can follow the perimeter. And the way it turns out to be real simple, the way you create a perimeter following mode is if you find the target that you're seeking directly behind you, switch to wall. You find what? Stay in wall following until you find the target you're seeking directly behind you, and you switch back to wall. And that works. Okay. So what will happen is it'll drive into this trap, this singularity trap, which it looks like we've already found here. Somebody point it back now. And it'll do this.
No, it's confused now. Its odometry is off.
I don't think so, man.
I didn't think about that.
It'll come forward, the IR or whatever it avoids, will turn it around, and at that point it'll find that the target is directly behind it, so it switches to wall following mode, and it'll follow this wall around until that point's directly in front of it, and it switches back to navigation. And that works very robustly. Okay. I think at this point, with y'all's indulgence, I'd like to take a little break, and then we're going to come back and we'll actually talk about grippers and grabbing soda cans and how the rest of this can be used to fetch cans. But I need to take a little break. I bet you guys are passing again. So I want to see if I can get this guy a little faster. We take maybe a 15-minute break. Would that be fine? Sure. But I want to demonstrate it before we get to the robot, and one of them was I just told it to stay inside of a 4 foot by 8 foot boundary. Yes, I set it 16 inches from the back, and so he should run around. But more to the point, I wanted to demonstrate how he can do the wall following behavior. The wall following is actually pretty easy behavior to do. You can do it with just bumper alone. If all you do is set up the robot so that it's always arcing to one side or the other. You say it's always arcing to the right, so it'll arc around until it hits the wall, the bumper will knock it off the wall, and it'll hit the wall again, and that way it'll follow the perimeter around the room. There's a couple of problems with doing it that way. Even if you turn on the IR, so we're not actually hitting the wall, we're just letting the IR turn us away from the wall. In particular, when you come to an outside corner, you may not be turning sharply enough so that, to actually follow the thing. So you'd really like to turn very sharply if there really is a corner, but not turn very much if there's not a corner. And in point of fact, if you swim along directly parallel to the wall, it'd be nice just to drive parallel, not to swim along it at all. So in order to do that, you actually have to know the distance to the wall. I don't call this wall following, I call it perimeter following, because the perimeter can be almost anything. It could be a group of people standing around, it could be foliage, it could be an abstract group of objects or something, as long as there's not a big enough gap for the robot to go through. So this guy, I'm going to let him finish out. He's supposed to run for 3 minutes and then try to find his way back right here where I mark. And I'm mostly doing this to illustrate that the odometry is not really that good, but it's good enough. It's good enough. It's not falling off the table.
Good enough for all practical purposes.
Every move is carefully planned. But obviously, you know, as you run the robot, the longer it runs, the more the odometry drifts because of wheel slippage and so forth. So you might be able to run it around one square that took 30 seconds and make it that bang on, you know, within 8 minutes or something like that. That's great. You can tell it's drifted to this side, but it's not coming very close to that, and it's coming quite close to this one over here.
So the perimeter following, you just put that in as a behavior, you write that code and then you...
It's just another layer in here. I can't remember exactly, I believe it's one level above the navigation.
So, and then as your user control, you basically turn that flag, that behavior on when you want to have it do that.
And in the case of the singularity, it can switch the behavior on and off itself, given certain modes.
Now, if you wanted to make the return to home more accurate, would you still just, the only thing you can do is eliminate the slippage, or would you use different type of methods to try to...
It turns out, when you really start looking closely, that's not bad. All right. Yeah, we're off. Now that was 3 minutes. We're off about an inch, maybe an inch and a half from where it started. For accuracy in the odometry, it turns out that you're actually measuring two things. You're measuring the translation of the robot and you're measuring the rotation of the robot. The translation value doesn't drift very much. The rotation, your theta, is what gets off. And that throws everything else off. Obviously, if you think you're driving in a space like this, but you're actually driving in a space like this, everything is off. But if you can keep the theta from drifting, then you can pretty well trust the distance. And that's actually what this robot does. The way it gets such good odometry performance outdoors is that it's measuring the distance across the ground with the odometry off the wheels. But the theta it gets from this inertial measurement device, which has got gyroscopes and so forth in it. So that the theta is very accurate. You can correct for the theta rotation. Pretty much the rest of it works fine. In the contest mode, this guy, robot contest course, would from time to time, because robot contests were always parallel walls. So he would from time to time stop and use the sonar, turn around and square itself up on that. And that way it's correcting the theta. And that turns out to be the one that you have to keep track of. That's the one that slips over the course of time. It's not really the distance traveled. It's the accurate rotation.
So do you find that the drift in theta due to odometry errors accumulating is
less or is different for the wheels than it is for a gyro?
Yes. They each have different problems. The gyro, in order to actually, they're rate gyros, so in order to actually know the heading, you have to integrate. The integration has errors over time. That's just like the same errors that you're getting by using the odometry. They increase over time. The way this guy gets around that is probably the subject of another day. There's a 3-axis gyro, a 3-axis accelerometer that's measuring the vector of gravity, and a 3-axis magnetometer that's giving you true north. And the problem with magnetometer, with any compass, is that there's errors. There's rebar in the floor and sort of stuff like that. But over long term, the compass is reliable. If you do a long-term average, it's reliable. It's short-term, it's wrong. The gyroscopes are correct on the short term, but their long-term average is wrong. So what we're doing is we're combining sensors here.
Yeah, with a complementary filter.
Yeah, and that way you end up with, essentially this gives me a vector which no matter which way the robot is pointing, it points at the North Star.
And I was just trying to connect that concept to the odometry and knowing your theta based on odometry and the drift.
Well, effectively what we're doing for the odometry is you get the theta from the inertial measurement.
I see. And you fix up the odometry.
Yeah.
I see.
Okay, well this guy has these, you're probably familiar with these little sharp IR sensors. They're pretty common. They give a distance out to about 16 inches and you really get a value back. It's a little parallax thing. That's the actual distance. So to do a good wall following, which we're going to try to do here, it's the blue LED. So you can see the IR turned us away. This may not work. I waited too long. This one does not have new batteries, unfortunately. Well, that will be for another day.
Dave, you want us to grab one of the foam boards and put it up on the table?
No, that's all right. The ability to do wall following is really, really powerful. To be able to follow a perimeter around, there's lots of different places that you can use it. So it's a real like fundamental behavior. In this case here, using it to solve the concave singularity, that's just one, but there's a lot of other cases in which wall following, good robust wall following. And this guy can do it real well, but not today. Okay, so we get to go back to this guy and have fun with canes. So this is these are things that are called emergent behaviors. Emergent behaviors is when you have several other behaviors that run that produce a behavior you didn't specifically program. A good example would be we've got a light over there and the robot is trying to make it toward that light with our photo behavior turned on. But there's an object, a wall in between. So the IR pushes you away from that wall. So you get this behavior where you swim along the wall with the IR pushing you away and the photo pulling you towards until you get to the end of the wall and then you turn toward the light. That's called an emergent behavior. It's a wall following that you didn't specifically program, but it arises from these other behaviors interacting with each other. We do can collecting, which I never tried to do or even thought about doing before the DPRG can collecting contest. Uses essentially all the behaviors we described so far in an emergent fashion. And it required adding a couple of new sensors, so I'll cover those first and then we'll come back. I described the sonar sensors earlier. They use these little little yellow LEDs. Let me turn them on here. And can you hear it? Those of you with good ears?
Yeah.
Yeah.
Oh.
Oh.
Yeah.
That's exactly what it is. So we're sending out, we have, these devices have about a 15-degree wide beam. Now, that's actually not totally true because the beam actually has these lobes on the side. But we're going to ignore them for the moment. And we're going to say that the beam itself is 15 degrees wide. And I've got two of them, and they're arranged so that the inner edge of them are coincident, like that. So here's the right beam and here's the left beam. You know, when you get a detection, you know how far away it is in inches, which is pretty handy. And you don't know where it is inside that code. but you know that somewhere inside the cone there's an object 28 inches away. But you know real precisely where the edge of the cone is. You can tell real accurately if there is something right at the edge, the inner or the outer edge of the cone. So that way you do know exactly where it is. And there's these coincident edges here. Well, let me just demonstrate. We'll start off just by having it drive around with just the sonar running and nothing else. It's these little yellow lights here. Sonar can see out to about 32 feet. I have it constrained here. It's only really looking out to about 12 feet. But its behavior is the same exactly as the IR behavior. And I'm just going to turn away from detection. It's just we can see things a lot further away now. It does have some blind spots because it can only see out to about 30 degrees. So really to make it robust, we also need to turn on the IR behavior so that if it's close to something, it can still respond to it.
Dave, isn't there also a minimum distance that you can see?
There is, although it's about 4 inches. And that's one of the reasons, if you look on this robot, this is set back about 4 inches from the front, so I can see things all the way up to the front bottom. But this one can't see anything closer than about 4 inches. Another way of saying that is everything closer than 4 inches looks like 4 inches. So to really make that robust, as I say, we really should turn on the IR as well.
Might differ from sensor to sensor.
How far away does the IR go?
IR can see out to about 18 inches. It depends on how bright the object is reflecting. If you have a nice bright white object that reflects the IR real well, you have a dark leather couch or something, it might not see all of it. It doesn't reflect so much. One of the advantages of the sonar sees it irrespective. But really the two of them have to run together in order to produce robust behavior.
How did the
Where
Polaroid?
you go?
Yeah. How do the Polaroid sensors work compared to the other
They work
sonars?
lots better. They take more power.
Are those Polaroid on the?
Yeah.
Yeah.
And as I say, they can see foliage, they can see chain link fences, and things like that some of the others have trouble with. Come on back down here.
That was you quick, Rich. You said the codec seems to pick up more stuff better than the other ones.
Yeah, they just work better. They take more power, but they, as I say, they can see foliage and they can see chain link fences and things like that some of the others have a hard time with. Okay. All right, so that's all. The sonar itself is a very complicated topic, and there's a whole lot to say. We spent all afternoon on sonar. I just wanted to demonstrate. That's its normal behavior, and I'm going to shut that off now, and we'll talk about these grippers a little bit. I built the grippers in order to do the DPRG can collecting contest. I've never done grippers before. I've never been really interested. I mentioned earlier that it actually screwed up the other side of the robot because this was all nice and smooth. There was nothing that could be caught, and I had a lot of ground clearance. But now there's these things that are just begging to hook onto whatever it is that's loose. The way that, let me set this up here, the way the grippers are designed, I spent some time thinking about this. If you have a gripper extended out in front of you and you grabbed a can, now you're driving along and you run into something. Well, we're back where we started from before we ever built the bumper. What do we do when we run into something? Well, one thing you could implement some sort of instrumentation on the gripper itself. So it would know whether or not it had run into things, and essentially you want to be replicating all the bumper behaviors. Another thing to do, and what I ended up doing, was just mount the gripper on the bumper itself. That way it inherits all of the bumper behaviors. Now this gripper can't pick up anything. It can't pick things up. It's designed to work with tennis balls and lightweight Coke cans. So really all it does is it can kind of constrains them when you push it around. If you had something really heavy,
The bumper would take over.
yeah, then you probably couldn't carry it because the bumper would be constantly being triggered. But it works for this case. So by attaching the gripper directly to the bumper, I don't have to do separate bumper behaviors. It inherits the bumper behaviors. The gripper itself is made out of 2 mini servos that are screwed to the back side of the bumper head. I don't know if you can see them, those little black boxes under there. Yeah. And one for each arm. And the arms themselves have a micro switch in it. I want you, these little things here that have a photocell and an IR for line following, ignore it. It does, actually it does a very cool line fall. We're not going to talk about it here. Because it can different size lines, it can close in on a real narrow line. Okay, and inside of each one of these, there is a micro switch, which tells when the gripper has grasped something. So mechanically, the subsystem is that we have a pair of servos that are driven in opposite directions, and the driver for this, what it does when it tries to grab something, it closes the gripper a little bit, and then it tests. Once again, it does this in 50 millisecond chunks. It tests to see if the switches are closed. And if they're not, it closes it a little more. And again, tests to see if they're closed. And if it continues doing that, if it can make it all the way to the center without the switches being closed, there's nothing to grab. So it opens the gripper back up. Now, how do you decide when to grab something? This turns out that this is a philosophical problem. It's not a trivial problem. And the solution I used here is to do what psychologists call a grasping reflex. Any of you who have babies have seen this. What a baby does is anything that touches its hand, it will grab. Mm-hmm. It doesn't actually make the conscious decision to grab something. It grabs anything it touches. It's up to the brain to steer the hand to the right thing. But the hand will on its own grab anything it touches. So that's what I'm doing here. These are bend sensors.
Yeah.
And yeah, they used to be everywhere. I don't know what happened. You know what these were? They were from a virtual reality glove. They were for your fingers, to show the bends of your fingers. It's kind of cool. But anyway, they have a variable resistance that changes when they're bent. And they're very lightweight. So this is my feeler for the grasping reflex. And the way the gripper works is that when something touches the feeler, we try to grab it. So we turn on the gripper, turn everything else on. Illustrate here that if something touches the bend sensor, that the gripper will try to grab. And if it can grip, it stops. If you pull that loose, then it drops it. So the robot itself never actually makes the decision to grab anything. It grabs anything it touches. The robot makes the decision to put things down, to let go. But it doesn't actually make the decision to pick something up. That happens automatically when the gripper is activated. Because it's driving this thing in and then testing for the switches, it can grab things of different size. So if we have the ubiquitous soda can, we can grab the soda can. Let's see if I can, if the can was bigger, let's say on its side, then we can grab it from the end. So the size of the can, actually, you know, I said it continues to close until the switches are full. In point of fact, it's a little more subtle than that. It continues to close a little bit after the switches are thrown. So it's a good grip. So it closes just a little more once the switches are thrown, so you don't drop it. So we can grab a can in any arbitrary orientation. Turns out that a lot of times when you try to pick up these cans, you knock them over. So those of you who try to know this, so it's good if you can be able to pick up the can no matter what its orientation is. And that's the way this thing is set up. Come back. Okay, so now we got a can. So what do we do with it? What do we do with that can? Well, one of the things I didn't get to illustrate because this guy wasn't working. When you ran the navigation, when you reach a waypoint, what you do is you select the next waypoint off the waypoint list, and that automatically begins your trajectory to the new one. But you can also, because you know how far away the waypoint is, because we're actually using odometry, you can actually slow down and stop when you get to the waypoint. And when you do that, you can do something else. You can do other things. What these robots do is, if they slow down and stop, the next thing they do is they fetch the next target from the target list, and they rotate toward that target before they begin the next path. It just simplifies the navigation if you're already facing where you want to go. Another thing it could do is it could put a can down if it had one. There's a whole list of things you can do when you reach a waypoint. So, here's what we're going to do. Start off, tell the robot Oh, let's get, where's my marker?
Need a coin?
Let's mark the floor here. There's our starting point. And we tell the robot, with its gripper turned on, it's the target of opportunity. It's obviously not having to find the can. Bam, we grab the can. Ooh, that's nice. And we just continue to go. All right? There's no navigation, there's nothing else running. But in a real life contest course, you actually want to do something with the can. And you remember that our routine that said, if we go to a waypoint, we can do something when we get there. Well, there's another one that's very slightly different. There's another layer that's running in here, which I haven't drawn. And what that layer says is, if there's something in the gripper, if the navigation is turned on, there's only one allowed destination. No matter where you are in your target list or how many targets there are in that list. If there's something in the gripper, there's only one allowed destination, which I call the default location. It could be anything. It's probably your recycling bin. In this case, it's just set to 0, 0. So if there is something in the gripper and the navigation is enabled, then you always go to the same location. There's another routine that says when you arrive at a waypoint, if there's something in the gripper, and if it's the default location, put it down. That describes the whole behavior. Well, let's try that. We start off and we say, we start the robot here, and I want you to go 8 feet forward and come 8 feet back. And somewhere along the line, you run into a can. Got the can. Whoa, new behavior. Lost it. There you go. Now we got it. Okay. So we rotate to our new waypoint. The default location is where we start. That's what it's currently set for. Suppose before we get back there with the can, I take it away. Well, it's no longer the default location. It's trying to go down there. Now, he's not looking for him yet. We've got to set him right out in front of him. Got a can. So we'll go to our default location, which is 0, 0. I won't take it away from it this time. And he gets to the waypoint. He's going to slow down and come to a stop. And he says, well, do I have a can? Yes, I do. Is this the default location? Yes, it is. Put it down. And then go about your business. Well, my business is to fetch the next waypoint, but we never reached the last one, so we're just going to stay with it. Now he's actually here. We'll let him get this one on the way back. So I really actually haven't had to write any more code to get it to do all this. All I had to do was add the gripper, and the gripper is self-functioning. It just grabs it. Notice he's counting the number of cans he has there. He said, I have 2. Now, you know, I said the default location is 0, 0, but I lied. It's 0, 0 plus 2 inches for each can that it collects. So that it'll put the cans in a line. And in fact, you can tell how much the odometry is drifting by how straight that line is. If the odometry is crooked, it'll put them in a different order. I also told it there's 6 cans out there, so it's not going to stop until it finds 6. Get it. Come on, it's right there.
Now it's chomping without it addressing.
Without
those are called targets of opportunity. If there's something out there that seems like a can, see if you can grab it. There's another rule that says, if the can is behind 0, 0, you can't have it. Now, because it tends to knock the cans over when it tries to grab them, because it's going at full speed, it would actually be useful if it slowed down. And we actually know how far away the can is, or we can know, because we have something. So this is real simple. Once again, we haven't changed any code, but what I'm going to do is I'm going to tell the sonar, rather than going away from a detection, go toward a detection. That's called negative sonar. Let's see if I can make that work.
Now, it doesn't have a way of knowing it is a can, right?
No, not at this point. Wait a minute. Must not be turned on. Got all the right switches thrown, yeah, no sonar. There we go. All the right switches. Once again, I'm just going to put it right out in front of it. If you see, now it sees the can, you see it slowing down.
We're going back and forth.
So the switches you have
Bam.
to turn sensors on and off?
Turning behaviors on it.
Okay.
I've got an enable switch for each one of these behaviors.
A switch, but there's also a software setup for which behavior. When you look at the screen and touch the.
No, they've just enabled and disabled, and I can set some parameters. All right, well, you hear the sonar ticking away there. And what it's doing effectively, there's another leaky integrator running, and we're looking to see if we can find the edge of that can. Every time we find the edge of the can, we throw something in that leaky integrator, so the robot slows down as it approaches the can, and it zeroes up on the can. You run into a problem if you hit a can way over here, that the gripper, when it tries to grab it, will just sling the can across the room.
Yeah.
So it'd be much better if you're actually zeroed onto it when you. So let's try that. There's just one other behavior, which unfortunately I can't illustrate in this room, where it can actually scan with the sonar and find the can. All right, so there's one. And you can see now it'll actually turn toward the can. It's not just a targeted opportunity. You're not done. What, do you think you only got one can? Notice that it doesn't grab that can even though it's touching it. It's behind the line. It's not a long can. You can't have that.
You want to put it on the other side. Oh, it's going to grab my can.
Yeah, he's coming after you. I can describe the other behavior, I can't illustrate it here. Effectively, we know the robot's location from odometry. We know the can's location because odometry plus the sonar, we can calculate the can's location. We can call that routine that says, is it inside a boundary box? And we can ignore anything that's not inside the boundary box. Robot contest course, the only thing in the course is can. So if you get a detection and it's inside the boundary box, it's a can. So what the robot will do is just do a 180-degree scan of the course. It throws away all the detections that are outside the boundary box. And it just stops aiming at any detection. Oh, for some reason he only thinks he's supposed to get that one can. So, for the larger contest then, there's a set of, it was always done in what was called a tea time course back in those days, which was a course 24 feet long, 16 feet wide in the shape of a T. Looked like this. And the robot would begin here, and the cans would be scattered around in this space. So it was given two boundary boxes, one this shape and one this shape, and told to navigate from here to here to here, back to here. And in the course of that navigation, anytime it finds a can, of course, it stops the navigation, takes the can back to the starting point. If it could make it all the way around this and back to the beginning, and it hadn't collected 6 cans or however many were in the contest, it just would continue that pattern. And each time he came and put down a can, it would actually perform this rotation. It would square up with the sonar on the wall. You can see this if you go to this website. I've got videos. Square it up so it knows its location very well. And then do this 180-degree scan looking for any detection that's inside of our boundary box. and just stop when it's pointed toward a camera.
Something.
And at that point, the rest of the behaviors take over. The sonar steers it into the can, it grabs it, and brings it back to the starting place. I think that's all I've got.
Very good.
Question, what do you think, how is can collecting helpful in terms of advancing club members' robotic understanding and the state of robotics in the club?
Well, it's, you know, it's an entertaining thing to watch it happen. I'm not sure I have a better answer than that to your question.
There are a lot of different skills that you need to master to be able to do it. It's not just...
Clearly, it's an advanced behavior, but some of things like square dance and Robo Columbus have to do with navigating with some precision and finding something. I'm looking, which you can think of as generally useful behaviors. And clearly, this navigation is a useful behavior generally. Just wondered if you had any thoughts on that. On the can collecting
requires navigation.
Yeah.
I think at this point, at least
To do the can, you really have to be able to do at least rudimentary.
that was exactly, the part I was trying to get to was that to get to this level requires all of these.
Yeah.
And that what looks like a fairly complex behavior is really not. It's really just a combination of some pretty simple behaviors. As I said, to do the can collecting, I didn't have to write a new code. I added this gripper on the front, and I made a couple of changes in terms of adding this default location to sequence or something in the gripper. But the rest of the behaviors are already all there. The can collecting is kind of fun. Let me see if I can get it to do a scan in here. I don't think we have enough room. I think it'll just
Grab the can and then come to
It's, where is and gripper and stop. Okay.
Dave,
Yeah.
how long did it take you from the time you started that robot to the time you got it essentially done?
About 5 years.
How many?
About 5 years.
So when you say simple,
It's relative.
And how low would you guesstimate?
This is, you know, this is a HC6011. It's only got 32K RAM. It's full. One minute.
5,000 lines of C code, maybe?
Probably
Not that. I'm just guessing.
Okay, let's see. It should do it. And that's my goal. Yeah, but I don't, evidently I don't have that functional here. I thought that's what this switch did. Oh, I can show you something fun here. I can show you this motion detector. It's fun. It decides when to set off the motion detector. It takes forever, so I'm going to tell it to do it by hitting my foot. Okay, so what it does, it's wandering around the house, it gets into a situation where it hits something with a bumper. Okay, and it does a 360-degree scan with sonar, IR, and photo, making a map of where the brightest and the longest and the highest IR are. And then it'll rotate toward where it thinks people are likely to be. That's a pretty good guess. And then it deploys its motion detector. And then it deploys its motion detector. Oh, wait. Here we go. Sorry, I didn't have all the right buttons pushed. Let's do it again. The algorithm makes this 360-degree scan. It figures people are likely to be where the bright light is and where the longest sonar is if there's no IR detection. All right. See, the motion detector can't see through that plastic front bumper. And it also doesn't work when the robot's in motion. So it'll sit there up to half an hour, and it actually plays a little, if you get real quiet here, it'll play a little song. It makes a little tiny sound, and then waits and makes another one. And one time I had it in my garage, and I just let it do that, and these crickets came out. I think they thought it was safe. See those little cells? See, and then it's waiting to see some movement, at which point it starts that process again. Now, there's always the possibility when it pushes that thing up that it might be underneath something, under a chair or something like that. So this is instrumented, so that it'll know if it comes up underneath something, which means that among other things, you can sneak up behind it. Figure out which way it's going to be. So where do you think the humans are? Same place. Interesting. Okay. Get back here where you can't see me. So it deploys the motion detector, and it takes a while for the motion detector to stabilize. And while it's doing that, if you move really slowly, you can tweak its nose. In which case, they can try to dig. I think with that, I'm done. Thank you so much.
I have a question. So it seems like you have a lot of knowledge into the psychology of robotics. Was this acquired by reading books, taking classes in college? I've never...
Just thinking about it and building a lot of them. I posted a message to the DPRG list a few months ago, which I was encouraging people. I said, play with your robots. Don't just think about it as something to do for a contest. And I think that a lot of epiphanies have come to me with that mint julep in my hand and my feet up, watching the robot wander around the house, or watching it get stuck. And instead of just jumping over and getting it free, saying, now how could it know it was stuck? How could it know that it got into that situation? What would be the proper response? If I had a radio control here, what would I do to get it loose? How can it know? And getting into those kind of state changes that are really problematic. Generally, what you need to do to escape is not so hard. That's not the problem. It's knowing that you're stuck. Knowing that you need to escape. That's where the challenge is. How to think about that problem. This robot has a real amazing behavior. I'll demonstrate one day. In that, because it has two ways to do odometry. It has an inertial measurement unit, and it also has the wheels. The wheels drift a whole lot more than the inertial measurement unit does, but they're both, on average, about the same. They're about the same. Over a long haul, they'll get way off. But, so if, on average, they're very different, something's wrong. Particularly if the wheels say, I'm spinning around, and the inertial measurement unit says, I think we're still. The wheels are slipping. So even though it doesn't have a physical bumper, it has ways of knowing that it's trapped. And it can respond in similar ways. And to say that the hard part is not knowing what to do. The hard part is knowing you're stuck. You're high-centered, wheels are turning, but you're not moving. How do you know that? That's really the hard part. Sonar can tell you some interesting things. If you're sitting there getting the same sonar readings over and over again, you're probably not moving. But there's a lot of ways to think about that. Knowing that you need help is the hard part. My name is David Anderson, and I approve this message.
By the way, a little comment. If you go to the dictionary and you look for attention deficit disorder, and then look at that definition, and then look at the antonym, you'll see a little picture of David Anderson.
Thank you very much, David. Thank you. Appreciate it. That's it. Thank you for coming, everyone.
Excellent.
Go